Okay, going to do a couple of problems on forces in circular motion. So this is chapter 6, multiple choice question 21. Multiple choice question number 21 at the end of chapter 6. In this, a ball on a string moves around a complete circle once a second on a frictionless horizontal table. That's sort of complicated, but they're doing that so you don't have to worry about gravity or anything like that. So I don't know, I could draw a table like this. Okay, that's the legs of the table or something. And there's a table here, and there's a ball swirling around on the table on a string, and that's a mess. But if we put our eye looking down above that table, what do we see? So I'm looking down on the motion. There's a ball that's traveling on a circular path at the end of a string. So this is the center of the string. Here's the ball. This is just showing the path that it's traveling. So at this instant, its velocity vector is that way. And it's frictionless. Gravity is going down into the paper, and there's a normal force coming up out of the paper, but there's no friction. And so the gravity and the normal force are perpendicular to the paper, and the only force in the plane of the paper is the tension in the string. So there's a tension in the string, and the question is, the tension is measured to be 6 newtons in the string. And the question is, the ball goes around, ball makes a circle, complete circle in 1 second. And the question is, what would the tension be if it took only half a second? For the ball to make a complete circle. So first we have to remind ourselves why there's tension in the string and how that relates to the motion. So if we cut the string, the ball's just going to go off in a straight line this way. The reason it follows that circular path is because the string is applying a force that keeps it from going this way and makes it turn, from the ball's point of view, left. And the string moves along with the ball, so it's constantly making it turn left, and it ends up following this circular path. The only force acting on the ball to make it go in this circular path is the tension in the string. Gravity is perpendicular to that circle. The normal force is perpendicular to that circle, so neither one of those forces affects any motion at all that's in the plane of the paper. Only the tension in the string does. That means that the tension is supplying the force, is the force that makes it go in a circle, and therefore that is the only force. If I define sort of the plane at this instant of the table to be the x plane, that would be like, we'll call it the xy plane with z coming out. If I now, let's imagine that I put my eye over here in the paper and I look at the ball going around, what do I see? I see the ball here, it's going away from me, and the string is going off to the left, and that's the direction that the tension is going. That's a terrible drawing, but there's the ball going away from me. So this is a top view up here, and this is an edge-on view here. So if it's traveling on a circular path at a constant speed, then the net force in the plane of that circular motion must be equal to mv squared over r. So the tension equals mv squared over r. Now I don't know what m is, and I don't know what r is. In fact, I don't know what v is. But I do know that this equals 6 newtons when the period of the motion is 1 second. And what I want to know is what is the tension when the period is half a second. So which one of these things changes when I make the period go from 1 second to half a second? I'm not changing the size of the circle, I'm not changing the mass of the ball, I'm changing how fast it's going around. In fact, I'm making it go around, instead of taking 1 second to go around, it takes only a half a second to go around, half as much time. That means the speed has doubled. The speed is now doubled. And that means that if I double the speed, since the tension is proportional to the speed squared, if I make v twice as big, t is 2 squared, or 4 times as big. So the new tension would be 4 times that, or 24 newtons. Alternatively, the speed can be related directly to the period. The speed is 2 pi r over, and I have to be careful here, I'm going to just write the word period, because they use a capital T for the period, but we're using capital T for the tension. So if the period goes from 1 to a half, then V gets twice as big. And you could make up numbers for M and R. You could say M is 1 and R is 1. T is 6 newtons. That would give you the original velocity. Then you could put that here, and you would see what happens when you change the period from 1 second to half a second and plug numbers in. But otherwise, you can just look at it proportionately and see that since the tension is proportional to the square of the speed, reducing the amount of time it takes to go around by a factor of 2 means I'm increasing the speed by a factor of 2. Increasing this by a factor of 2 increases this by a factor of 4. If V goes from 1 to 2, V squared goes from 1 to 4. So the tension is 4 times bigger. Let's take a look at number 23. Number 23, we've got a race car with a little inverted wing, and that is to increase the normal force, and the increase of the normal force increases the possible frictional force. So again, this is in the multiple choice question section for chapter 6, and in this case the question says a car can go around a half circle with a diameter of 190 meters at 68 meters per second. So let me draw a half circle. And we're told that the diameter is 190 meters. And I've got a car traveling around there like this with a speed of 68 meters per second, and the mass of the car is 610 kilograms. The approximate static friction force to complete this turn is, so we're asked, what is the static frictional force necessary for the car to complete this turn? Well, just as with the previous problem, this is a car traveling at a constant, an object traveling at a constant speed on a circular path. There's we're looking down on the car, so there's gravity into the page. There's the normal force out of the page. Those are perpendicular to the motion of the car, so they're not affecting its motion at all. If I'm traveling on a circular path, then there must be a net force towards the circle, center of the circle, and it's static friction between the rubber and the road that's providing that force that enables this thing to go on a circular path. Imagine if the car were on an icy road and you try to drive around in a circle this fast. You can't. You'll just go in a straight line. You can check some somewhat amusing videos on YouTube to see cars sliding around in the winter. They have no friction that allows them to direct which way they're going. So it's the friction that enables that car, pushes that car on this left-hand turn around in a circular path. So again, looking edge on, if I put my eye down here, this is my sketch of an eye, looking up the paper at the car, what do I see? Here's the car, it's going away from me, and it must be accelerating towards the center of that circle if it's moving on a circular path, and so it's the static friction force that's providing that. So that static friction force has to equal m times v squared over r if I'm traveling on a circular path with a constant speed. Well, I'm given m, 610 kilograms, v, 68 meters per second, and r, the radius of the circle, is just half of the diameter, so r is d over 2. That's 95 meters. Everything else I'm given, so the static frictional force is just 610, that's the mass, times 68 squared, that's the velocity, divided by 95. And get out the calculator, 610 times 68 squared divided by 95 equals, and I get 29,700 newtons. And to two significant digits, that's 30,000 newtons. Okay, so the static frictional force adjusts itself to be what it needs to be for the motion that's happening to occur. So you're driving the car, you're determining the speed, you're determining r. If static friction is large enough to make you go in that circular path, it will increase to be whatever that value is. Now, as an aside, just to take this a little bit further, the maximum value that static friction can be is mu sub s times the normal force. Well, what is mu sub s for rubber on concrete? From a table in the book, that's 1.0. What's the normal force? Well, if we go back to that edge-on view and we do a full free body diagram, we've got static friction towards the center of the circle, we have a normal force up, we have weight down, and then the beginning of the problem mentions wings on race cars, push them into the track. So Formula One cars, they have an inverted wing on them, and instead of lifting it up like it lifts a plane, this pushes the car down, and you'll see why that's necessary. So assume that there's an additional force down, I'll call F wing, that's pushing down on the car. What that does is, because the car is not jumping off the road or sinking down through the road, the sum of the y forces, this way is y, this way is x, equals 0, and that means n minus w minus f wing equals 0. The weight is just m times g. For this car, that's 610 times 9.8. 610 times 9.8, which is 6,000, roughly, newtons. Now, if there was no wing pushing down on that car, 6,000 newtons down would be balanced by the normal force, which would be 6,000 newtons, and Fs max would just be this coefficient of 1 times 6,000. That's a lot less than 30,000 newtons. So this car could not go around such a sharp turn so fast, that's well over 100 miles an hour, without something else pushing it down to give a larger normal force. So in this case now, I have a normal force that's equal to 6,000 plus F wing, and since I know that my frictional force is equal to 30,000 newtons, that means I've got to have at least 24,000 newtons greater than or equal to 24,000 newtons from the wing so that the normal force is at least 30,000 newtons, so that my frictional force can be that large. So that means most of the force down into the road, for this case, is not coming from the weight of the car, but from that inverted wing.